Swayam Prabha. Digital India. Educated India.
Okay, so if you see it, the improvement diminishes with the use of fine, more cohesive materials such as zeolite and cement powders due to phenomena such as powder bridging, compaction and agglomeration. Now, let us see the pressurized powder feed system. As you can see here in the diagram, there are various parts like orifice bypass is here, high pressure air goes into this system and this is the oscillating valve active when nozzle valve open this particular part, and here is the mixing chamber where air and abrasive particles from the container coming in through the orifice and they are getting homogeneously mixed up, and after mixing they go through the tube or the pipe and come over here in the nozzle, and this is the bottom part of the nozzle through which the air abrasive jet comes out. Now, the powder is fed to the air stream from a pressurized reservoir through an orifice and mixing chamber. This is the pressurized reservoir, this is the powder level shown over here, and it is fed through the orifice. The system utilizes an oscillating valve that splits the operation cycle into two halves. This is the oscillating valve. Whenever it is open, the air can go in, and if it is closed, air does not pass through this. The operation cycle is activated by a switch only after the entire system including reservoir has initially been pressurized by closing the nozzle end and opening the oscillating valve to the main air supply. When this is opened, this is closed over here and then this is activated. During the first half of the cycle or the operation, the oscillating valve is open, allowing air to flow from the pressure regulator to the mixing chamber. Air will flow from here to this mixing chamber, while some enters the powder reservoir and the rest flows out through the open nozzle, right. So, this is how it is going to work, and once the mixture comes out of this nozzle, it hits the workpiece surface as we have already seen. Pressurized powder feed system continues. It is during the first half cycle that any powder that has entered the mixing chamber is forced out of the nozzle. In the second half of the cycle, the oscillating valve is closed, stopping air flow through the system. At this point, the reservoir is still pressurized, but the mixing chamber is at atmospheric pressure due to the open nozzle. Nozzle is open, so the mixing chamber is at the atmospheric pressure. This creates a pressure differential that forces the powder down through the orifice at the bottom of the reservoir and into the mixing chamber. So, from this it comes over here when here the atmospheric pressure is there in the mixing chamber and this is at the very high pressure. So, because of pressure differential of pressure, the powder is forced through this particular orifice and it comes into the mixing chamber. That is how the powder is coming to the mixing chamber. Air is coming from there, from this particular side, and this they mix up over here in a proper way. The oscillating valve then opens again and the cycle is repeated. So, the limited control of the powder mass flow rate is possible by regulating the air flow rate through the reservoir and by changing the orifice bypass and the size of the reservoir orifice. So, this is how you can control to some extent the powder feeding rate to the mixing chamber, and then that mixture passes through the nozzle. Fluidized bed powder spray system, this is the another system. In this, as you can see over here, this is the nozzle, this is the pumping pressurized air over here, and you can see this is the reservoir having the powder over there. Fluidizing air is passed through this, and you can see that whole system. In this system, upward high speed air flow from the bottom of the reservoir through the powder bed creates a cloud of suspended particles. This is the cloud of the suspended particles, some of which settles into a collection funnel at the top of the reservoir that is connected to the air stream leading to the nozzle. This is the air stream and this is leading to the nozzle over here. The mass flow rate could be regulated to some extent by changing the diameter of the funnel. Diameter can be changed and to control the mass flow rate, because larger the diameter, larger the flow rate, but again other parameters will change. So, you have to be careful while changing the diameter of the pipe. Fluidized bed powder spray is operated at significantly high powder mass flow rate than the pressurized powder feed system. This is the pressurized powder feed system we have already seen. So, in this particular case of fluidized bed powder spray, the high powder mass flow rate is obtained compared to the other system which we have already discussed. The powder mass flow rate obtained by the fluidized system decreases rapidly as the powder in the reservoir is consumed. Once the powder in this reservoir is consumed, then the level keeps going down, and as a result of that, the mass flow rate keeps on decreasing in this particular pipe towards the nozzle. So, you have to fill up the reservoir with the abrasive powder to have higher mass flow rate. So, this has to be taken care of properly. Now, factors affecting constant powder feeding: powder compaction. This phenomena usually happens in pressurized powder feed system. The powder is firmly compacted during the course of abrasive jet micromachining process. By such way, cavities often form in the vicinity of the orifice, likely causing variations in the powder mass flow rate as the cavity walls collapse, randomly injecting bursts of powder into the nozzle. So, you can see different parts over here that we have already seen, and this is the shaft, and this is the Teflon blade is there in the shaft, and this is the orifice, this is going to the nozzle. This part we have already seen, this is showing high pressure shaft seal. In order to reduce powder compaction in the reservoir of pressurized powder feed system, the system can be modified by mounting a variable speed rotary electric mixer above the reservoir with the shaft passing through a pressure seal bearing that had been mounted into the reservoir. So, this will mix up, this will vibrate this or make the movements in the powder, and this will give a better flow rate of the powder to the mixing chamber and then to the nozzle. So, this kind of the modification can be made in the earlier system to improve the performance of the powder flow system. Now, factors affecting constant powder feeding continues. Effect of reservoir powder level, as at some part I have already shown to you that as the reservoir powder level goes down, the flow rate, mass flow rate of the powder goes down. The powder flow rates in the fluidized system were an order of magnitude higher than in pressurized system. The fluidized system gives much higher mass flow rate of the abrasive particles compared to the pressurized system. It is found to have good repeatability when the powder level in the reservoir is maintained at a constant level. So, the basic requirement or condition for the fluidized system is that the powder level in the reservoir should be maintained constant if you want to have constant mass flow rate in case of fluidized system, and fluidized system gives higher abrasive mass flow rate as compared to the pressurized system. Powder stratification, powders stratify as they flow and it depends on particle size. So, the control of the particle size distribution is also important, because if you say the particles are of 10 micron size, no, it will be having a certain range of the size of the powders in that particular, and that range should be as narrow as possible to avoid this stratification. And mixing time does not appear to affect the degree of particle stratification significantly. Therefore, the powder size distribution changes while blasting, as the smaller particles are ejected first, leaving the larger ones to remain in the reservoir. That is why I just mentioned that the range of the powder size distribution should be as narrow as possible, so that you get uniform abrasive mass flow rate. However, in most practical applications, a relatively small amount of powder is used during a single machining operation, and therefore, a negligible change in powder size distribution occurs. So, you can say that distribution or the change in the powder size distribution is small, but still many times you have very accurate work to be done. In that particular case, you should have as small variation in the particle size distribution as possible, so that you get the proper accuracy. Nevertheless, to ensure repeatable results, the powder reservoir should be emptied and refilled with fresh powder often, so that many times the powder remains adhered to the sides of the reservoir. So, to avoid all this and to make it fresh or refilling, you should clean it and refill it with the fresh powder, so that the performance of the abrasive jet micromachining is constant and repeatable. Again continues it, powder humidity is very important aspect. Mechanical properties of powders are influenced to a large extent by the humidity. Hence, drying of the powder and drying of the air, both are very important. Increased humidity decreases the fracture toughness, which can have a large effect on resulting solid particle erosion rates. This is very important. So, powder as well as air both should be dried before they mix in the mixing chamber in the system. Humidity can also greatly influence the powder flowability. Definitely, agglomeration takes place, then flowability is significantly affected and it reduces and it becomes random, and the repeatability of particles mass flow rates. Definitely, when agglomeration is there, mass flow rate repeatability will be reduced or it will be very poor, since it has a direct effect on interparticle adhesion. So, to avoid this, humidity in the abrasive particles and air should be as small as possible. To minimize these effects, sacks of desiccant were placed inside the sealed powder storage bottles, and both a desiccant based and a refrigeration air dryer were used to dry the compressed air. So, removal of humidity from the air as well as the abrasive powders is important. So, various measures are taken to take care of it, just like desiccator as he mentioned, and achieving a moisture free powder reservoir however is difficult because of its frequent exposure to atmospheric moisture when it was open to be refilled. That is right, but its attempt should be made to minimize the moisture contained, and that can be done, and this effect can be minimized by ensuring that powders are left in the reservoir for the minimum amount of time. That means, before restarting an operation, after a certain period of time, you should refill the powder in the reservoir. That is what was mentioned little earlier also. The ease of mixing device also presumably helped in breaking the particle-particle bonds caused by moisture. So, particle-particle bonds should not be there, or they should be minimum in the powder. Now, let us look into the results that have been obtained by different researchers. Only some of them are discussed over here. There are large number of research papers available on this subject. Some of them I am giving you at the end of this talk. So, you can refer them, and these results have been taken from those reference papers, just like paper number 16 given over here. I have given at the last slide what is that paper number 16 or reference number 16, from where all these results have been taken. Now, you can see here these are the abrasive per area grams per centimeter square, and this is the mass loss per area in terms of milligram per centimeter square. Now, as abrasive per area are increasing, the mass loss of material is also increasing. Now, you can see in all the three cases, these three cases are for three different materials. This is for copper, this is for stainless steel, and this is for zinc. So, you can clearly see that as the properties of the workpiece material are changing, the mass loss per area is also changing. Harder the workpiece material, lower will be the mass loss per unit area, and that is what you can see here. Here this stainless steel is having lowest one, and zinc having the maximum one, which is the softest in all the three cases, and copper being in between. So, you have the in between mass loss of the copper per unit area. So, you should try to understand this phenomena with the help of the physics also. You connect it to the equation which I had given you earlier, and you will find that lower the hardness of the workpiece material, lower will be the higher will be the mass loss per unit area. Same way you can see here abrasive per area, and here is the mass loss per area, and this is for different elements like Ultra Pro, Resist, Image Pro, and Rapid Mask. So, different kind of the mass area is over here. Change in mass during blasting. So, that you can see in both the cases, again taken from the reference 16. Now, surface observations after blasting, Image Pro, single impact in resist, different materials are there, Pro material resist is there, SU8 is there, and ripple surface on Ultra Pro. Now, you can see here the kind of the material, the cavities that are being formed on different materials, you can see over here and you can see over here. So, for all the four cases, different kind of features have been created by using the abrasive jet micromachining process. Again, here you can see erosion rate in terms of milligram per gram, and particle velocity is given in terms of meter per second. Now, you can clearly see here that as the particle velocity is increasing, in all the three cases erosion rate is increasing, because I have already told you that the kinetic energy that the abrasive particle will have will be proportional to half mv square, where m is the mass of the abrasive particle, v is the velocity. As the velocity increases, square of it is affecting the material, will be affecting the material removal rate or erosion rate. So, you can clearly see that erosion rate is proportional to the velocity of the abrasive particles. Now, again erosion rate is here for different kind of the materials, and you can see the slope are given over here. So, these slope will depend upon the properties of the workpiece material and the properties of the abrasive particles. So, abrasive particle, higher the velocity, higher will be the erosion rate. Both it also affects the erosion rate on the mask, because as I have mentioned earlier while discussing mask, that mask is also subjected to the abrasive particles to some extent, and erosion rate of the mask should be minimum, otherwise it will affect the properties of the features being created. It may have the larger dimensions, and it may or may not be possible to correct those dimensions, so the part may get rejected. So, you have to be careful in selecting the particle velocity and designing and deciding the mask material. Erosion rate dependent on material hardness for several particle velocities. You can again see over here, hardness is here, hardness of the workpiece material, and this is the erosion rate, and for different particle velocity 219 meter per second, 201 meter per second, 167 and 116. The phenomena that you have to observe here is that as the workpiece hardness is increasing, the erosion rate is decreasing, which is obvious. Harder the workpiece material, lesser will be the erosion rate, and this is what you can see again taken from the reference 16. Now, it is again the hardness and erosion rate for different velocities. Now, one thing is there, you can see here that there is a certain velocity at which you find minimum erosion rate, then beyond that velocity the erosion rate keeps on increasing. So, for 160, and this minima is different, more or less the same in this particular case for 167 and 160 meter per second. So, beyond this particular hardness, the erosion rate is continuously increasing with increase in hardness. Surface quality dependent on particle velocity. Now, this is a copper, stainless steel and zinc. So, you can find all the three and same phenomena, particle velocity increases, surface roughness value Ra is increasing in all the cases. The reason being, larger the material removal rate or erosion rate, larger will be the surface roughness value. So, it also tells us that for having a good surface finish or lower surface roughness value, you should have lower velocity. However, material removal rate or erosion rate will go down, but this will be you can, if your requirement is good surface finish, then you have to compromise with the material removal rate also. So, you can see 4 different pro: rapid mask, image pro, ultra pro and raised, and you can see in all the 4 cases the erosion surface roughness value is coming to be different with different mass. So, you have to study this and you have to select a proper type of the mask, proper type of the particle velocity to get a surface roughness, desired surface roughness value. Imaging accuracy, let us see. Now, you can see here A and B are 1 millimeter hole in steel and resulting under etching in glass after blasting with 0.8 megapascal. So, you can see this is the 1 millimeter hole A and B in steel. So, you can see the kind of the edges, circular edges here, all this, and this is another part of the hole, you can see clearly. And C is the electro grown 0.3 millimeter structure in zinc after blasting with 0.8 megapascal. So, this is there. Now, you can clearly see the point which you should try to understand here is that this is the main feature that was to be created, but all this portion which you see here from here to here, this is the flaring effect. That means the jet flares out, and because of that you do not get the uniform removal of the material in the whole area. Only here where central peak is there, the jet is like this, something like jet is something like this, jet velocity is something like this. So, wherever you have this highest velocity, you get this part, and wherever you have this diminishing velocity, you get this flaring part. That is why flaring should be minimum possible, but you cannot avoid it because the density of the air is very low compared to the water. We will see when we discuss abrasive water jet micromachining or water jet micromachining, you will not get this kind of the flaring effect, and this definitely changes the characteristics of the machine feature. And then fourth one is the widening of image pro after blasting with 0.4 megapascal. This is what you wanted, but again flaring effect is seen over here, and such effects should be minimized. And second thing is, you can see here, this is not very repeatable or constant diameter. You can see here it is extending beyond this particular range and so on. So, all these these are, although they are in micron size, but you have to see to what extent you can accept them as a feature in the device, because they are going to affect the performance of the device. Repeatability of powder mass flow rate in pressurized system, consecutive trials using sampling times of 2 seconds, 5 seconds, 10 seconds and 120 seconds. Now, this is again very important graph. You can see here they are mass flow rate, this is the mass flow rate and this is the trial number. So, repeatability means if it has a very good repeatability, then these curves should be a kind of a straight line if it is absolutely repeatable. But you can see all the 4 curves like this curve. Now, in different trial, in this particular trial it has the minimum mass flow rate, in the first trial it has the maximum mass flow rate, and if you see this particular one, you know, this is varying like this and having minimum one in the 8th trial and then increasing, and here also it is having minimum and then increasing. So, such kind of behavior is not very good, because it is going to affect the performance of abrasive jet micromachining. That is very important to be noted. However, unless there are the design changes, you cannot get a constant flow rate as such. Mass flow rate as a function of powder level in fluidized system, that I had mentioned to you, that the fluidized system, the reservoir, in the reservoir the level of the abrasive particles should be maintained constant, otherwise the mass flow rate is going to change, and that was mentioned at that point of time also when I was discussing that particular slide. So, you can see here the powder height above bottom of reservoir is given over here. Now, as the powder height of the bottom above the bottom of the reservoir is increasing, that means the level of the abrasive powder in the reservoir is increasing, the mass flow rate is also increasing. Although it is not a straight line, if you see it here, it is slightly changing beyond 150 millimeter as the height of the abrasive powder bank or reservoir in the reservoir. So, you have to have the constant mass flow rate, definitely you have to maintain the height at a constant level. If it is fluctuating, then your mass flow rate of the abrasive particle is also going to fluctuate, and this you have to take into consideration very carefully, because if mass flow rate of the abrasive particle is changing, as we have seen in the earlier slide, then erosion rate is also going to change, and that is very important to check that erosion rate does not change, otherwise it will be very difficult. Now, here you have the Laval nozzle design. This is important to understand. Now, let us see, this is the inflow. Now, this is the bottom plate of the nozzle, this is the middle plate, and there is the upper plate also, which is not shown over here because it has been taken out, so that you can see cross section inside that particular one. So, this is the inflow air inlet here as well as here. So, air is being supplied through these two ports, and from this port abrasive particle is coming, that is abrasive inlet, and this air and abrasive particles, they are coming in this particular tube, that is the mixing point over here, and this is, you can call it mixing duct or mixing tube over here, and these abrasive and air particles mixed up over here, and ideally they should have the homogeneous mixture, but in real life it is not like that, and this mixed air abrasive particle jet comes out of this orifice and it goes to the to hit the workpiece surface. Now, you can see here that as the nozzle length is increasing, the duct width is also changing over here in this particular case, and this is giving you what is the air inlet is here, throat is there at this particular nozzle length, mixing point is here, and this particular nozzle length and orifice is there. So, you can find this design in the reference number 32. I will stop here. Thank you very much.